Hello students, let us take one problem on steady state stability. The problem is that the motor torque is given, the equation is T equal to 1 plus 2 omega m, where the load torque is given by Tl equal to 3 square root of omega m. So these are the motor and load characteristics. You have to obtain the equilibrium point or points, and you have to determine the steady state stability, where the points are stable points or these are unstable points. So as you know, for stability, for equilibrium points, the motor torque becomes equal to load torque. So let us start it at equilibrium point. T is equal to TL, that is 1 plus 2 omega m is equal to 3 square root of omega m. Let us square on both sides. So it will be like this square. So you can write it as 1 plus 4 omega m square, 4 omega m square plus 4 omega m is equal to 9 omega m. So just it will form a quadratic equation, 4 omega m square minus 5 omega m plus 1 is equal to 0. Solve this equation and you will get 2 points. Solving, we get omega m is equal to 1 or omega m is equal to 0.25. So there are two solutions of this quadratic equation, omega m equal to 1, omega m equal to 0.25. So this point let me call equilibrium point A, and this point we may call as point B. So let us see whether these 2 points are stable points or unstable points. You can show it graphically also. If you plot these 2 characteristics, it will be somewhat like this. So you have to take T on this axis because it is equation in this form. So the load torque is linear. So the motor torque is a linear torque. So it is varying from 1. Starting point is 1 plus 2 omega m. So this is the load torque, the motor torque, and load torque is 0 at 0 speed. So it is somewhat like this. Let me use a different color. So it is starting like this and it is somewhat like this. So the 2 solutions that we have obtained, this is at omega m equal to 0.25. The other solution comes at omega equal to 1. So these are 2 solutions. So this is this point omega m equal to 1 I have called point A, and this I have called point B. Now you have to check whether these points are stable points or these are unstable points. So let us apply one method where we have seen that for stability, dTL upon d omega m should be greater than dt upon d omega m. If this condition is satisfied, you can say that the point is equilibrium, a stable point, otherwise the point is unstable point. So let us apply this method first. So let us find out what is dt upon d omega m. dt upon d omega m. Differentiate this equation. It is equal to 2. And what about dTL upon d omega m? So it is equal to 3 into 1 by 2 into omega m to the power 1 by 2 minus 1, that is minus 1 by 2, and you can write it as 1.5 upon square root of omega m. So dt upon d omega m remains constant at equal to 2. Let us try to find out the value of dTL upon d omega m at 2 points. So at point A, dTL upon d omega m at point A is equal to 1.5 upon square root of 1, that is 1. It is equal to 1.5, which is less than dt upon d omega m. This means that this point is not a stable point. So this point is unstable. Now at the other point, that is dt upon at point B, dTL upon d omega m at point B, where it is equal to 0.25. So its value is equal to 1.5 upon square root of 0.25, and this value comes out to be 3. So this is greater than 2, that is dt upon d omega m. So you can conclude that point B is a stable operating point. So point A is unstable and point B is stable. This means that the motor will run stably at point B, that is at a speed of 0.255 radians per second. So in that way you can find out steady state stability, and you can determine whether the point is stable or it is unstable. You need not to go for that method that we discussed earlier. In this situation, just use the equation and try to find out the solution. So in that way you can try other problems also that I will provide in the tutorial sheet. Thank you for today.